if we're going to evaluate this, I'm going to walk up to this integral and I'm going to think to myself, can I make it look like x is raised to powers? And I can't right now because that stuff in parentheses on the bottom, I can't do something else with. My next line of defense is to look for a u substitution. And on this one, this is not the only way to manage it, but I would choose to let u be x minus 3, which makes du dx. And I'm going to go ahead and change the bounds for my limits as well. So when x equals 4, u would be 4 minus 3 or 1. And when x equals 10, u would be 10 minus 3 or 7. So when I switch all of that around in my u sub, I'm going to go ahead and take my 2 out in front. My limits would be from 1 to 7. And this would look like 1 over u squared du. Doing the u substitution just puts me back into a frame where I'm going, oh, hey, can I make that look like u's raised to powers now? And I can. We can rewrite that to look like u to the negative 2 so that I can find the antiderivative, add 1 to the exponent, divide by the new exponent. I've still got that 2, and then we're going from 1 to 7. Because we had limits of integration, I don't have to go back and plug x's back in because we already converted the numbers. We can just go ahead and plug the numbers in. I'm going to choose to think about this piece, though, as really saying negative 2 over u. That negative in the exponent means my u is in the bottom, and it doesn't matter where I put the negative 1. So I'm going to get negative 2/7 minus negative 2 over 1. I just walk away. But you could get a common denominator and do that subtraction. So I've looked at the exam solutions. Oh, actually, before I forget, I'm going to actually say words out loud here. And I am attending some meetings in Washington, D.C. this week, which means I'm leaving early tomorrow morning to fly to the East Coast, and I will be out Wednesday, Thursday, Friday. So we won't have co-class on Thursday, but I will post videos of kind of where we're going next, which is going to be area between curves. Today we're going to talk improper integrals. If we have time, we might do some area between curves, but I'm not sure we're going to have a ton of time. Got some kind of e to the negative x, and I want to go from 0 to 5. And just go ahead and find that area in there. And I'm going to go ahead and let you find that area on your paper. I'm going to give it a shot. I'm not going to do a u substitution because I just have that antiderivative rule memorized that if I have e to a number times x, when I take the antiderivative, I'm just going to divide by that number. So this would look like e to the negative 2x divided by 2. And then we're going from 0 to 5. So if I plug in the 5 first, that's e to the negative 10. Instead of dividing by 2, I'm just going to save myself a little bit of space and write that as a times 1/2 minus 1/2 e to the 0. By the way, what is e to the 0? Okay. So really, that's just 1/2 e to the negative 10 minus 1/2. What if I told you that I didn't actually want to find the area between 0 and 5? I actually wanted the area between 0 and 50. What's the only thing that would change my answer down here? And what would my exponent become if I was really going all the way to 50? My purple pen does not want to work today. So if I was going 0 to 50, what would my antiderivative look like? Minus a half. And what if instead I told you, I don't actually want to go to 50. I want to push this thing out as far as I possibly can. If I'm going to push that thing out as far as I possibly can and think about tools we had in 17A, what's all the way out here? Now, I can't actually really just plug in infinity. The way we've been dealing with infinities all along in calculus is to think about that as a limit. So what I'm going to do instead is I'm going to put up a wall right here. I'm going to put my wall up and call that A. And I'm going to write what my integral would look like to find that area from 0 to A. Now, before I actually do this, should have made you do it before I had written anything down. Okay, pause for a second. I just want you to think about it logically. I'm going to find the area under that curve from 0 to infinity. What should the area add up to? Some people think it's probably going to be pretty big because I'm adding it up from 0 to infinity. Yes? Some people think someone might even guess that it's going to be infinite because I'm adding this up from 0 to infinity. It's like I've got an infinite number of little rectangles. I'm adding them all up. Okay. Let's actually do it. So I'm just going to go from 0 to A at the moment. We already know what the antiderivative is. We're going to get 1/2 e to the negative 2x. We're going from 0 to A. Let me know if I get off the screen too far. Which means I'm going to have 1/2 e to the negative 2a minus, we know when we plug in 0, we get 1/2. And then we do the mathematician thing and say, we didn't really want this to be at A. We wanted to push it all the way to infinity. And pushing it all the way to infinity means I need to take the limit as A approaches infinity. How do we feel about limits? You gonna answer that one on your own? We're gonna do that one together? You got it. Okay. So, couple of different options for how to deal with this. But sort of our first line of defense anytime we're looking at limits is to just plug the number in. So if I plug in infinity, infinity times 2 is still really, really big. What's e to the negative infinity? Cool. When we have negative exponents, another option is to write that in the denominator. So suppose that instead I wrote that as 1/2e to the net to the 2a. Oh, someone in the chat has pointed out that I have made a mistake all the way along here. Like from the beginning. I forgot a negative sign. Okay, I'm going to chase my negative sign through. Thank you for catching it. This should have been divided by a -2, which would have made that a -2, which I guess we could say would have made that positive, which would have made that a -2 and would have made that positive and would have made that a -2 and would have made that a -2 and that positive. So that's positive and that's a -2. Thank you. Okay, I have chased my minus sign through. Now we're ready to actually evaluate it. One more time, what did you all say this is equal to? So I've got infinity in the denominator. So 1 over infinity is going to, yeah. So this actually turns out to be 0 plus 1/2. You don't have to think that's weird. How many people can at least relate that mathematicians might think it's weird that we added up an infinite amount of stuff and got 1/2? It's kind of a big deal to mathematicians. They think it's pretty cool. It's intriguing. It's interesting. It's the kind of stuff that makes people want to be math majors. Okay, not me, but other people. Makes other people want to be math majors. That we just added up an infinite amount of stuff and we got an answer of 1/2. So the whole idea with improper integrals is that usually we're headed to some kind of asymptote. We're either thinking about an asymptote because we're headed to positive or negative infinity, or we have a situation where we have some kind of vertical asymptote and interesting things are happening. And when we do this and we look to find those areas, sometimes we get what we expect. And when we do the integral, it all adds up to infinity. And sometimes when we do the integral, surprising things happen and we actually get a number. And when we get a number, we put a label on it and we say that this converges. And this time, oh, by the way, 1 over x has 2 asymptotes. It's got this asymptote as x approaches infinity of 0, but it's also got this vertical asymptote of 0. And this time, what I want to look at is the area in here from 0 to 4. Similar to the other problem, can I actually plug 0 into the function? So anytime I've got an asymptote happening, whether it's in the function or because my limits are infinity, it's an improper integral. So if I were writing this as 0 to 4 of 1 over x dx, from here on out, anytime you have a definite integral, you've got to pause for a second and ask, are either of those limits going to be a problem for us? Are either of those limits going to say something about an asymptote? And because 0 is going to say something about an asymptote, we have to pause and rewrite this using limits. I'm not going to be able to actually plug 0 in. So I'm going to build myself a fence. And then I'm going to push that fence towards 0. It doesn't change anything in terms of like how we evaluate the integral. The only thing it does is gives us a last step where we're going to plug in numbers and deal with the limit. So if I integrate 1 over x, what do I get? I'm gonna put my absolute value on there, even though I know if we're just going from 0 to 4, I know the numbers are positive, but I'm gonna put my absolute value on there anyway. And then we're going from a to 4. And I've got the limit as a approaches 0. Now, if I wanted to be really precise about this, all of the numbers between 0 and 4, all of those x values are a little bit bigger than 0. So I could write this with a plus on my 0 to indicate that I'm coming One way to think about it is to indicate I'm coming from the right. I like to think about that as saying 0 plus a little bit, because all of the numbers between 0 and 4 are like 0 plus something. Again, I'm going to plug in my 4, subtract off, plugging in A, and then evaluate the limit. First thing I'm trying with any limit problem is to just plug it in and see what happens. Well, there's nowhere to plug it in on the ln of 4. So that's just going to remain ln of 4. And natural log of 0 is headed to negative infinity. Which means overall, this thing is going to infinity, and we say that it diverges.
So you know the limit goes to infinity for ln of 0 because of the graph.
Well, not this graph, but because of a graph with natural log of x. So here's y equals ln of x. So as x approaches 0 from the right, that function is going to negative infinity, because the answer to a limit problem is like, where's the y value headed? Not gonna lie. Okay, I'm gonna walk up to this integral. It's a definite integral, so I'm gonna check, does this integral involve asymptotes? And it does, because my limits have a negative infinity and a positive infinity. So actually, we're talking about 2 asymptotes here. So one of the other things that we need to know about improper integrals is I can only manage one limit at a time, which means for this problem, I actually have to break it up into 2 pieces so that I can address the limit for the part that's going to negative infinity and the limit for the part that's going to positive infinity. Are there any other places where we're going to have vertical asymptotes? Meaning, is the denominator ever 0? Yeah. So we're going to be fine. X squared plus 1 isn't going to have anything happening. So we can choose any number at all we want between negative infinity and positive infinity. Someone tell me their favorite number. 7? You got it. So we're going to break this up. And we are instead going to write this as going from negative infinity to 7. And from 7 to positive infinity. The mechanics of working through an improper integral, I still have to be able to find the antiderivatives of whatever they throw at me. So I'm not going to worry too much about the limits now that I've kind of got it broken up. I'm just going to ask you all to find the antiderivative of x over x squared plus 1 whole thing cubed. Just a little bit of practice. We'll come back together to do the limits piece on our own. We'll do the limits piece together, but go ahead and find the antiderivative of that on your own. So I think when I add 1 to my exponent, divide by the new exponent, make sure I get my minus signs right this time. I'm going to be dividing by -2. So I could write that as -1/4 u to the -2. And I'm going to make that -1 over 4 times x squared plus 1 squared. If we were really just finding the antiderivative, I'd have the plus c here, but I know that we actually are going to put in limits of integration. So now let's pull it all together notation wise. So I'm going to have the limit as it really doesn't matter our choice of letters, but I'm going to call this first one. I'm going to rewrite this to swap out my negative infinity for an A and let A approach negative infinity. And I'm going to swap out my infinity over here for a B and let B approach positive infinity. So when I come down here, I'll be looking at the limit as A approaches negative infinity. I'm going to have this function, but I'm plugging in 7 and A. So I'll have -1 over 4 times. It's like I meant to do this, but actually Joy just picked her favorite number. What's 7 squared? And 49 plus 1 is 50. What a lovely number to get to square. It worked out so well on accident. That's me plugging in 7 minus me plugging in A. And then we're adding that to the limit as B approaches positive infinity. -1 over 4 times B squared plus 1 whole thing squared minus -1 over 4 times 50 squared. Now we're ready to take the limits. Sometimes when we do this, one part of this will go to infinity and the other part will go to a number. If that happens, what's infinity plus a number? Right, so we would still say that it diverges. So if we've broken it up into pieces and any of the parts go to infinity, we get to be done and say, nope, that was infinite. It's not going to happen to us this time though. So when I plug in the negative infinity, there's nowhere to plug it in here. So this just comes along for the ride. When I plug in infinity here, infinity squared is infinite. Adding 1 to that doesn't change it. Squaring it again, still infinite. I've got a number over infinity, so that's headed to 0. Looking at the piece back here, same kind of thing's going to happen when I plug in the infinity. I'm going to have 1 over infinity. That part's going to 0. And I didn't get infinity in my final answer, so I get to write the word converges. Let's do that. So I know that because I've got the negative infinity and positive infinity, we do have a problem. We are going to have to break this apart. So there's kind of 2 pieces to this. I have to deal with the limits and I have to deal with the integration. So I'm going to go ahead and deal with the integration first this time, and then we'll deal with the limits. So let's just work on that antiderivative. So I am looking at x squared over 9 plus x to the 6th dx. First thing I'm going to ask myself, can I make it look like x is raised to powers? We can't because of the addition down there in the denominator. So then I might be thinking about a u substitution. So I look at that and say, well, the derivative of the bottom would actually be x to the 5th. So that doesn't sound like I've got a u substitution. I personally wouldn't go to integration by parts because it's just algebra. And if it's just algebra, I'm hoping there's something else I can do. It's a fraction. The power on top is smaller, so it's not going to be long division. And the bottom doesn't factor. So it's not going to be partial fractions. But there is an algebra trick that we can do to make a U substitution magically appear. And now I've got a U substitution that's going to magically appear for us. And if I allow U to equal x cubed, then du would be 3x squared dx, and 1/3 du would be x squared dx. And this whole thing would turn into 1/3 1 over 9 plus u squared du. This one happens to be an arctan. So I know that we think of arctan as being 1 over 1 plus u squared. But our textbook actually gives us, sorry, I'm trying to pull it up. Two different versions for arctan in section 4.6, which is about antiderivatives. Our book gives us that the integral of 1 over 1 plus x squared dx is tan inverse of x plus c, but 1 over a squared plus x squared dx is 1 over a tan inverse of x over a plus a constant. And it's that second version for arctan that really is showing up for us here, because that 9 I can think about as saying 3 squared. Okay, so that's what I'm working with. I'm going to rewrite this. Coming back to here, I know that the A is going to be 3 because that's what's squared kind of in this formula. So I'm going to have, when we take the antiderivative, I'm going to have the 1/3 because it was already there. And then I'm going to have another 1/3 because it's part of the formula. Tan inverse of x over 3. Sorry, it's not an x, it's a u. That's why my pen is red at the moment, because I'm writing it in u's. And I would have a plus c, but we're going to have limits of integration. So I'm not going to write my plus c on. But I am going to fill back in what my u was. So this is 1/9 of tan inverse of x cubed over 3. And now we can address our limits. So the whole thing was going from negative infinity to positive infinity. Since both of those limits cause a problem, we have to choose a number in between. And I am going to choose 0 because I'm going to choose something that I know the value of arctan for. So I am going to break this up and say that we were going from a to 0, with a headed to negative infinity. I'm just rewriting the original. Plus you're taking the limit as b approaches positive infinity, 0 to b. And now that we've got our antiderivative ready to go, we can plug that in and look at the limits. When I plug in 0, I'll have 1/9 tan inverse of 0 minus 1/9 tan inverse of a cubed over 3 plus the limit as b approaches infinity. I am somehow going to squeeze this all in. I'm going to put b in first. So 1/9 tan inverse b cubed over 3 minus 1/9 tan inverse of 0. Okay. Now we have to know some things about arctan. I don't think very well in arctan, but like if you are good with what the graph of arctan looks like, awesome. When I think arctan, I'm really coming back to if I have tan inverse of x and I don't know what that's equal to, the other way to think about this is that x is equal to tangent of what angle? So what's the angle where tangent is equal to that thing inside the arctan? So what's the angle where tangent is 0? Yep. So I'll just go ahead and put zeros for both of those. Now I'm going to put in the negative infinity part. Negative infinity cubed is still negative infinity. Divided by 3 is still negative infinity. So this is asking what's the angle where tangent goes to negative infinity? And that one, maybe we want to think about what the graph of tangent looks like. So I've got a negative pi over 2 and a pi over 2 on that tangent graph, and it kind of almost looks like a cubic inside. It's not quite, but has a similar shape to that. So the angle where tangent is going to negative infinity is negative pi over 2. You could choose to just memorize that as a number, or you can think about it from the graph. Now over here, when I plug in positive infinity, I end up with 1/9 tan inverse of positive infinity, which is asking the question, what's the angle where tangent is headed to positive infinity? And the angle on that is pi over 2. So I'd have 1/9 times pi over 2 minus 0. So I've got pi over 18 plus another pi over 18. So I think my final answer here is pi over 9. And I'm going to add in the word converges because we didn't get infinity.